Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about how to find the empirical formula of a compound that's formed from reactants that are in the gaseous phase, and we're given the pressures. So let's get into this. So in this problem we're told a xenon fluoride compound can be prepared by heating a mixture of xenon and fluorine to a high temperature in a pressure-proof container made of nickel. Assume that xenon gas was added to a 0.25 liter container until its pressure was 0.12 atmospheres. Fluorine gas was then added until the total pressure was 0.272 atmospheres. After the reaction was complete, the xenon had been consumed completely, and the pressure of the F2 or the fluorine remaining in the container was 0.36 atmospheres. So note that all the pressures were measured at the same constant temperature. What is the empirical formula of the compound prepared from xenon and fluorine? Okay, so things to notice. We're asked for the empirical formula of a substance that's formed from xenon and fluorine, and it's a xenon fluoride compound. So if we write the equation, basically we're adding xenon gas plus fluorine gas, and that's going to produce some compound that involves both of these together in the compound, in the formula. So it's going to be xenon with, we'll say, subscript A, and fluorine with subscript B. So this is the equation. It's not balanced because we don't know what A and B are, but we're asked to find the empirical formula. Anytime that you're asked to find the empirical formula, you have to find the moles, because remember, the subscripts in the empirical formula are mole ratios. So if you can get the mole amounts of xenon and fluorine, then you can get the lowest whole number ratio from those moles. So that's always the goal, is to get moles for the empirical formula. Okay, so next let's write down all the information they're giving us. So here they're giving us a volume of 0.25 liters. So we have volume is equal to 0.25 liters. Also, we're told that the pressure of the xenon is 0.12 atmospheres to start with. So if we write that down here, let me give myself some room here. So we're starting with atmosphere 0.12 atmospheres here. And again, I'll write over here, so volume is equal to 0.25 liters. Okay, and then they say that the fluorine gas was then added until the total pressure was 0.72. So total pressure, I'll write that down, the total pressure is equal to 0.72 atmospheres. Okay, after the reaction is complete, the xenon was 0.36 atmospheres. So that is the pressure of xenon. I'll write that in a moment. We'll come back to that. And then they're telling us that temperature is constant. So we'll write that down. Temperature is constant. Okay. But also keep in mind that volume is constant as well. We're told that this reaction is taking place in a pressure-proof container. That means that this is a solid, rigid container. It's not going to flex. So therefore, volume is going to be constant as well. So that's going to be very helpful in understanding what we can do here. And let's go over. So let's start with the combined gas law, and I'll show you why this is important. So if we start with the combined gas law, that would be P1 V1 over N1 T1 is going to be equal to P2 V2 over N2 T2. Okay, so again, this is the combined gas law. And one of the things you should know is that this is really the only law you need to know because all the other laws will come from this because, or I shouldn't say law, but I should say the equation. This is the one of the equations you should know. All the other equations come from this because we can eliminate from this equation anything that's constant. So if it's constant, we can eliminate it, and then whatever's left identifies the equation we need to use for whatever problem we're trying to do. So, so if volume is constant and temperature is constant, we can get rid of them. So here, volume 1, volume 2 cancel out, and then temperature 1 and temperature 2 cancel out. And what are we left with? We're left with P1 over N1 equal to P2 over N2. And so why is this important? This is important because notice what happens. So the pressure and the number of moles are directly proportional to each other. So such that, notice here that the ratio of my beginning pressure and amount. So if I start with a certain pressure and I start with a certain amount of the number of moles, then that's going to be a certain ratio. If I change the pressure, then the number of moles has to change in order to keep the ratio the same. They have to change in the same way. So for example, if I double the pressure, in order to keep the ratio the same, I would have to double the number of moles. If I half the pressure, or if I take half of the number of moles, if I half the number of moles, then I have to half the pressure. So why is that important? Because this tells us that the pressure and moles are directly proportional. They're proportional to each other. So that means that pressure is going to be proportional to the number of moles. Well, why is that important? Well, notice that they didn't give us moles in the problem here. We have this equation and the coefficients and all that are mole ratios, right? These we think of these as moles. But under these conditions where pressure and temperature are constant, that leads to the situation of pressure and the amount of gas being directly proportional to each other. So therefore, even though they didn't give us moles, because pressure is directly proportional to moles, we can treat pressure like moles. So the atmospheres they give us, we can treat that as moles and do our table. We can do a little stoichiometry table here and figure out what's going on. Okay, so now that I've got that out of the way and I explained that, hopefully that helps. So be on the lookout for situations like that that make your problem a lot easier. Okay, so now we can go to the equation and I can do my ICF table, where I stands for the initial starting materials, what we start with. C is the change, and F is the final amounts that we end with after the reaction. So we're told that prior to the reaction, 0.12 atmospheres. The pressure, that was the pressure of, what was it? Xenon gas. So that's what I have here. So 0.12 atmospheres of xenon gas. We're then told that fluorine gas is added to the container until we get a total pressure of 0.72 atmospheres. Okay, so we have 0.72 atmospheres total. Well, this is a mixture of gases. This includes fluorine plus xenon, right? So what's the pressure of fluorine to start with? Well, that's going to be the pressure of the total pressure minus whatever this pressure is, the pressure of the xenon, right? So if I write this here, so total pressure is going to be equal to the partial pressure of xenon plus the partial pressure of fluorine according to the law of Dalton's law of partial pressures. So Dalton's law of partial pressures tells us that the total pressure is equal to the two partial pressures of the gases mixed together. So since we know the total pressure is 0.72 atmospheres, that's going to be equal to the pressure of xenon, which is 0.12. So 0.12 atmospheres plus the pressure of fluorine. So to find the pressure of fluorine, all I have to do is subtract out the pressure of the xenon, 0.12 atmospheres, from the total of 0.72 atmospheres. So then I subtract 0.12 atmospheres from both sides, 0.12 atmospheres. And so then I end up with the pressure, the partial pressure of fluorine is equal to 0.60 atmospheres. So that was the beginning pressure. That's the starting pressure of our fluorine. So we can now put that here. So 0.60 atmospheres of pressure. And of course, we don't have any atmospheres of pressure because this has not been formed yet. Okay, so this is where our beginning is. And so now we can fill in the rest of the information. So we're told that after the reaction was complete, the xenon had been consumed completely. So we don't have any xenon left over at the end. So our final here is 0. We end up with 0. Well, what's the change? We started with 0.12 atmospheres. We end up with 0, so the change is negative 0.12. We're subtracting that out. So we lost 0.12 atmospheres of pressure. Okay, let's keep going. So the xenon is consumed completely, and the pressure of fluorine remaining in the container is what? 0.36 atmospheres. So at the end, our final pressure of the fluorine is 0.36. So let's write that down. So we have in the final 0.36 atmospheres. Okay. Now we can figure out the change here of our fluorine because we know what the initial is, we know what the final is, and so again, we figure out what that is. So if we subtract this, if we do the final minus the initial, right, what we ended up with, then what we end up with for this is, and I'll write it over here, final was 0.36 atmospheres. Subtract out the initial, which was 0.60 atmospheres. And when you subtract the 0.60 from the 36, you get negative 0.24 atmospheres. What does the negative mean? It means we lost that much during the reaction. So then this is negative 0.24 atmospheres. Okay, so now we have the change in both of these after the reaction has gone to completion. And our limiting reagent is the xenon because it went to zero. We lost all of it. So this went to completion. We ran out of this first. So this is the amount of atmospheres. This is the atmospheres. This is the amount in pressure of the xenon that ended up in our formula. Also, this is the amount of the fluorine atoms that ended up into our formula. Okay, now we could use that, but also look at this. Notice the relationship between the loss here and the loss here. So we lost 0.12 atmospheres, right? We lost fluorine 0.24. What's the relationship between 0.12 and 0.24? Do you see it? They're double. So for this amount of xenon that reacted, I have a double amount of fluorine that reacted. So the ratio between xenon and fluorine that end up in the fluorine is 1 to 2. So this tells us what the coefficients are in the balanced equation. So for every one amount, right, of my xenon, I lose double the amount of my fluorine F2. So that means this is a 2. So the ratio here is 1 to 2 based on the change. Well, what does that mean? This should be a balanced equation, right? So according to the law of conservation of mass, the same number of atoms I have on this side should be the same on this side. So therefore, since I have one xenon here, I should have one xenon there. So that's going to be Xe. Notice I have 2 times 2 atoms of fluorine. That's 4 atoms of fluorine on this side. So I should have 4 atoms on this side. And there's the formula of my compound. Okay, so simply based on this and the ratio of the change in both of these was able to identify what the ratio here, what the coefficients are, and that helped us figure out what the number of atoms are in there. Now, that's one way to solve this problem. Now, if you didn't notice that, if you missed that, you could still solve this by taking these two as molar amounts, right? Okay, so this is a second way that you can solve this if you miss this part. If you didn't catch this, you could still get the right answer by continuing. So how do you get the right answer? So I'm going to erase this, okay, and I'm going to erase this because we don't need that anymore, okay, and this I'm going to erase so I can get some room here. Okay, so this here is going to be key. Remember what I said about the proportionality between pressure and the number of moles. Well, since I know, because this is the change in the atmospheres, this is the amount of the xenon that ended up in my formula, and this is the amount of fluorine that ended up in my formula. Now remember, the main way, the usual way that you find an empirical formula is to convert what you're given to moles. And then and then you write the pseudo formula, and then you basically reduce to the lowest whole number ratio and all that. Well, remember, if the pressure in atmospheres is proportional to the moles, we can treat atmospheres like moles and use our balanced equation, or not I shouldn't say the balanced equation, use the formulas to convert to moles of the atoms, right? So let's go ahead and do that. So here I have negative. We'll just do the 0.2, not the negative. So 0.12 atmospheres, right? We can treat that like moles, right? So we'll call that moles. And then we can use the ratio here, right? So we have, for every one of these, obviously I have one mole, right? So this is the 1-to-1 because it's just an atom. So simple enough. So then this means that this 0.12 moles of this is going to be equal to 0.12 moles of the xenon that ended up into my formula. And then I can do the same for fluorine. So then for fluorine, the amount that ended up in my formula over here is 0.24. So then if I take the 0.24, and again, instead of atmospheres, I treat that as moles. We'll call that moles. And here, I want to convert to atoms because remember, I don't have fluorine molecules in my formula. I have fluorine atoms. So I have to convert this to fluorine atoms. So here is the amount of fluorine molecules that was put into there, but it was put into there as atoms. So we need to convert this to fluorine atoms. So we know that for 1 mole of F2 molecules, right? That's going to give us 2 moles of fluorine atoms. So F, because you see here that one formula of F2 gives us 2 atoms. So then I just double the number of moles. So this is going to be 0.48 moles of fluorine. So now I have the moles of xenon and fluorine. So now I write my formula with these here as subscripts. So remember, the subscripts in your empirical formula are the moles. Here I have moles. So I start by writing my pseudo formula. So I'm going to have Xe with 0.12 as a subscript, followed by F fluorine with 0.48. 0.48 is my subscript. So here is the moles, my subscripts, but I don't like this number. Remember that in your empirical formula, the ratio should be 1 to something. And the way you get 1 to something is by dividing both of these by the smallest number. So since 0.12 is smaller than 0.48, we'll divide everything by 0.12. Notice here that I get my 1. And then when I divide by 0.12 over here, 0.48 divided by 0.12 is 4. So then my formula is XeF4. So you would end up with the right answer if you continued in the normal way by taking the amounts of the atmospheres as moles that was put into your formula, and then converting it to the moles that you need of each atom, and then writing the pseudo formula, dividing by the smallest number, and then making sure you have a whole number ratio of 1 to something. And so that's it for the empirical formula. I hope you enjoyed this video. If you enjoyed the video, if you really enjoyed and you learned something and this was helpful in any way, then please like the video, share the video, hit that like button over here somewhere. Also, help me out. Subscribe to my channel. Hit that notification bell somewhere around here. And when you do, make sure you click all so you can be notified by any videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question that you need help with, or if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.